Welcome you all in lecture number 34 of Abstract Algebra MTL 6051. In this lecture, we are again going to discuss what is the irreducible polynomial, and what is the Einstein criteria, for irreducible polynomial, examples of irreducible polynomial, and Galois theory, Galois field, and construction of Galois field. Okay, so let us see first the definition of the irreducible polynomial. If R is integral domain, a non-zero non-unit, see non-zero non-unit polynomial fx belong to Rx is said to be irreducible if fx is product of two polynomial hx and gx, gx and hx both are in Rx. Okay, then either hx or gx is unit. Okay, then fx is irreducible. Okay, see for example 4 plus 2x square, fx is equal to 4 plus 2x square. This is equal to 2 into 1 plus x square, sorry 2 into 2 plus 2x square. Say this is gx and this one is hx. Okay, this gx is unit in Q, so this fx is irreducible in Q, irreducible in Q, but gx is not unit in Z, gx is not unit in zx, then gx is not irreducible, sorry fx is not irreducible in zx. Okay, similarly 8 minus 2x square, 2x square plus 4 and x square minus 2. Okay. Now see the Einstein irreducibility criteria. What is Einstein irreducibility criteria? If fx is equal to a0, a1x and anx is an polynomial in zx, right? It means all the coefficient a0, a1 up to an are in z. If there exists a prime number p such that p divide a0, p divide a1, p divide an minus 1, right? Prime number divide a0, a1 up to an minus 1, but the prime number p does not divide an and p square does not divide a0, then fx is irreducible over Q. So let us see some example based on Einstein irreducibility criteria, right? See, for this example, compare this fx is equal to a0, a1x, a2x square, a3x cube, a4x to the power 4, okay, plus a5x to the power 5. What is a0? a0 is equal to 2, a1 equal to 6, a2 equal to 0, a3 is equal to 4, a4 is equal to 6 and a5 is equal to 1. If we consider p is equal to 2, then this 2 divides a0, 2 divides a1, 2 divides a2, that's so on, 2 divides a4, 2 divides a3 also, 2 divides a3, 2 divides a4, but 2 does not divide a5 and 2 square does not divide a0. Okay, so by Einstein irreducibility criteria, fx is irreducible in Q. Okay. Similarly, the second example and third example, x square minus 2 is irreducible. Okay, why x square minus 2 is irreducible? See, x square fx is equal to what? X square minus 2. Then fx can be written as x minus root 2 x plus root 2, right? It is irreducible, right? Sorry, gx and hx. Then this fx is irreducible over Q, but reducible in R. Okay, set of real number. Okay. Similarly, if fx is equal to x square plus 1, later on we will discuss these two examples in detail. Let's see, x minus I, x plus I. Okay, these two factors are in C, so it is irreducible in R but reducible in C. Okay, reducible in C. So let us see some important result regarding to these two examples, and later on we will discuss these two examples in detail. See, if f is filled, what is f? F is filled and a is not 0. A is not 0 element of f. And what is f? F is filled. Then the result says that if f of x plus a is irreducible in f, then fx is irreducible over f. Okay. A into fx is irreducible, then fx is irreducible over f. F of ax is irreducible, fx is irreducible over f. Okay. What is fx? See some example. Fx is equal to x plus 1. Now, see this example. Fx is equal to x square plus 1. Irreducible over q. Let 1 belongs to q. Okay, 1 belongs to q. Then, what is fx plus 1? Fx plus 1 is equal to x square. X plus 1 is square plus 1. That is x square 2x plus 2. Let p is equal to 2. Right? Then p divides a0, p divides a1, but p does not divide a2. And p square does not divide a0. Okay? Then by EIC, fx is irreducible over q. Okay, fx is irreducible over q. Now come to this example. Fx is equal to 1 plus x square plus x to the power p minus 1. See, if fx is equal to 1 plus x square, that is 1 x to the power p minus 1. This can be written as x to the power p minus 1 divided by x minus 1. Okay. So, what is fx plus 1? Fx plus 1 is equal to x plus 1 whole to the power p minus 1 and divided by x plus 1 minus 1. Okay. So, this is equal to 1 by x 1 plus x whole to the power p minus 1. Okay, and this is equal to 1 by x. What is this? pc0, pc1, that's 1, pcp x to the power p minus 1. This one is cancelled out. and 1 by x, and write this thing pc1 pc2x dot so on pcp x to the power p minus 1. What is pc1? P. What is pc2? P into p minus 1 divided by 2 into x dot so on. What is pcp? 1 into x to the power p minus 1. So if we consider p as a prime, then p divide this. Okay, then p divides. If we consider p as a prime, then p divide this. P divide this, right? P divides everything, no, except 1. P does not divide 1, and p square does not divide p, this thing. So by Einstein irreducibility criteria, this given polynomial is irreducible over Q. Okay, this is irreducible over Q. Now see, fx is equal to 1 plus x square is irreducible over Q, right? Solve it. Okay. And this thing, apply this result. F of minus 1 into x, that is 1 plus x square dot so on x to the power p minus 1. Now replace x by minus x by minus x. Okay, and this polynomial we already shown that it is irreducible. Okay, so by the result, if f of minus 1 into x is irreducible, then fx 1 minus x square minus x cube, right, plus x to the power p minus 1 is also irreducible. Okay. Yes. Now come to the next example. If fx belongs to zx and degree of fx is 4, then fx is irreducible over R, right? What is fx? Fx is in zx. Okay, degree of fx is 4. Degree of this fx is 4. So by fundamental theorem of algebra, this fx have 4 roots, right? This fx have 4 roots. Then this fx have 4 roots. Then the roots of fx, since we have to show that it is irreducible over R, it is reducible over R. Let us assume that it is irreducible. Then what happens? Then if it is irreducible, then this polynomial fx have no roots in R, means fx have no real root. Okay, no real roots, right? If fx is irreducible in R, if it is irreducible in R, then what is the roots of this? Roots of this are complex number x equal to a plus minus b and c plus minus id. Okay, this thing. Okay, then x minus a, see this, then x minus a minus ib, x minus a plus ib, x minus c minus id, x minus c plus id is equal to fx. Since what is roots? Roots are alpha 1 2 is equal to a plus minus ib, and beta 1 2 is equal to c plus minus id. Then what is fx? Fx is equal to x minus alpha 1, x minus alpha 2, x minus beta 1, x minus beta 2. Okay, this is fx, right? So this fx is equal to x minus a square plus b square. Similarly, x minus c square plus d square, and this is equal to x square minus 2ax plus a square plus b square, x square minus 2cx plus c square minus d square. Okay, so this is gx and hx. So neither gx nor hx is unit in Rx. Hence, polynomial fx have degree 4 is not irreducible over R. Okay. Now see some another important result. If f is filled, see, if f is filled, then every single polynomial in fx is irreducible over f. Okay. Okay. Every single, if f is filled, then every single polynomial fx is irreducible over. Okay. Now come to the another example. Fx is equal to x square plus 1 is irreducible over Z7. We are talking about the finite field. Okay. See, if fx has no roots in Z7, then this polynomial is irreducible. What is the element of Z7? Element of Z7 are, what is Z7? 0, 1, 2, 3, 4, 5 and 6. Okay. What is F0? F0 is 1. What is F1? 2. What is F2? 5. What is F3? F3 is equal to, what is F3? F3 9 plus 1 10, that is 3. What is F4? 16 plus 1 17, 17 divided by 7, 3. F5, it is 25 plus 26 divided by 7, that is 5. F of 6, 36 plus 1, 2. So these elements are not 0. These are not 0. It means fx doesn't have any roots in Z7. Fx doesn't have any roots in Z7. So fx is irreducible over Z7. Right? But see what the proof written here. Let us assume fx is irreducible. Then it has two roots, a and b. Right? Since it's second degree polynomial, then x plus a, x plus b is equal to x square plus 1. And this thing is x square plus a plus b, x plus ab. Right? What is a plus b? Compare left and right hand side. Okay, left hand side and right hand side. A plus b is equal to 0. And what is ab? Ab is equal to 1. When a plus b is equal to 0, when the ordered pair are either 0 0 or 1 6 or 2 5 or 3 4. Okay, then whether their product is 1 0 0, product of 0 0 is 0, product of 1 6 is 6, product of 5 2, that is 10, 10 divided by 7, that is 3, 4 into 3 12, 12 divided by 7, okay, that is 2. Okay, so AB, product of AB never become 1 for these ordered pair. Okay, so these two equations will not satisfy simultaneously, okay, in Z7. Hence this polynomial x square plus 1 is irreducible over Z7. Okay. Next, if fa does not equal to 0, a belong to ZP. See, fa does not equal to 0, a belong to ZP, which we already discussed. Na? Then fx is irreducible over ZP. What is fx in our previous example? X square plus 1. So f of a does not equal to 0 for all a belong to Z7. Okay. It means what is fx? Fx x square plus 1 is irreducible over Z7. It is irreducible over Z7. Okay. Okay. But this result is true the polynomial up to degree 3. So no, it is a small exercise for all of you. Find the degree of polynomial, find the polynomial whose degree is 4, right, which satisfy this condition also, but which is irreducible. Okay. Next, if f of a equal to 0, if f of a equal to 0 for some a belong to ZP, then fx is reducible over ZP. Okay. If f of a equal to 0 for some a belong to ZP, then fx is reducible over ZP. Okay, see this thing, fx equal to x square plus x plus 1. What is this? This is irreducible over Z2. Why? Fx equal to x square plus x plus 1. Then what is f of 0? 1. What is f of 1? 1. Both are not 0. It means it is irreducible. Similarly, x square plus 1. It is irreducible? No, it is reducible. Why? Fx, if fx equal to x square plus 1, it is irreducible in Z2, but it is reducible in Z2 but irreducible in Z7. Why? Since f of 1 is equal to what? 2. What is 2? 2 is 0. So it has 1 roots in Z2 but no roots in Z7. It is reducible in Z2, right? But irreducible in Z7. Similarly, this one, f of a does not equal to 0. F of a does not equal to 0. Sorry, f of a equal to 0 for some a. For some a belongs to Z11. Right? Put the value of x 0, 1, 2, 3 up to 10 since it is Z11. Right? So either f0 is 0 or f1 is 0 or f2 is 0 or f3 is 0 or dot so on, f10 is 0. Any one must be 0. So it is reducible. Okay. Similarly, this is reducible. This is reducible in Z3. Okay. Whether x cube plus 1 is irreducible in Z5. Okay. What is x cube plus 1? X plus 1, x square minus x plus 1. Okay. So this is what? Minus 1. Minus 1 divided by 5. Okay. This is 4. So x plus 1, x square plus 4x plus 1. This x cube is written in this way. Okay. This is irreducible. So see that this polynomial does not have any roots in Z5. So it means f0 does not equal to 0, f1 does not equal to 0, f2 does not equal to 0, f3 does not equal to 0, f4 does not equal to 0. Okay. Okay. Now come to the new topic, that is the Galois field. What is Galois field? See, what is Galois field? If f is finite field, what is f? Remember that. What is f? F is finite field. Okay. And order of f equal to p. What is f? F is finite field and order of f is p. And fx belongs to fx is irreducible. Okay. Since f is finite field, so its order is finite, and we are saying that its order is p is the prime number. Okay. And fx belong to capital Fx, which is irreducible polynomial. Then the structure ZPX Fx, right, is field, and of course finite field of order p to the power n. Okay. What is n? Degree of this polynomial. Fx belong to capital Fx is irreducible, and degree of Fx is equal to n. Okay. So this is finite field of order p to the power n. Okay. And what is the element? The element is written in this way. A naught, this is not p, sorry, this one is x. A naught a1x, a2x square, dot so on, an x to the power n plus, you can write it in separate way, a naught a1x, a2x square, dot so on, an x to the power n, such that all ai belong to ZP. A naught up to an belong to ZP, and sorry, this thing is polynomial this thing can be written as a naught a1x dot so on, an x to the power n plus fx, and ai belongs to ZP, okay, and AI belongs to ZP, and this A naught, A1, AN, this belongs to ZP, okay, plus Fx. This ZPX by Fx containing this type of element, okay, just like in group G by H and ideal in factor group G by H and factor ring R by I. What is the element of G by H? Element of this is A plus H, where A belongs to G. And what is the element of R by I? That is A plus I, where A belongs to R. Similarly, element of this is the polynomial from ZPX plus Fx. Okay, this thing. So we have to construct the Galois field of order 4, order 9, order 8. Let us see how we will construct the Galois field of order 4. See, it is the Galois field of order 2. Right? What is the Galois field of order 2? Galois field of order 2 is Z2x by Fx, and element of this is A0 and Fx. Now, what is the order of Z2x by Fx? It says that order of this is 2, and we know that order of this is 2 to the power n. What is n? N is degree of Fx is equal to 2. It means what? N equal to 1. It means degree of Fx equal to 1. Degree of Fx equal to 1. Okay. Then x plus 1 is irreducible polynomial. Irreducible polynomial in Z2. Why? Why this is irreducible? Since we know that every first degree polynomial, this is first degree polynomial, is irreducible over the field. And what is Z2? Z2 is field. First degree polynomial and Z2 is field. So it is irreducible. Okay. Then this first degree polynomial is irreducible over Z2. Okay. So consider Z2x by x plus 1. What is the element of this? This is A0. Means every polynomial of Z2 is divided by x plus 1. Then we got the remainder constant term. Constant term we denote A0 plus x plus 1. Okay. And what is A0? A0 is either 0 or 1. Is the element of Z2. Okay. So the element is 0 or 1. So A0, 0. 0 plus x plus 1 and 1 plus x plus 1. It is the field of order 2. Okay. Galois field of order 4. Z2x 1 plus x square. See, 1 plus x square is irreducible over Z2. Remember that. 1 plus x square is irreducible over Z2. An element of this, since it is second degree polynomial, and whatever be the remainder means what? Any polynomial over Z2x we divide by 1 plus x square. Then we got the remainder term in first degree. And first degree polynomial is written here. A0 plus A1x plus Fx. Okay. What is A0 and A1? A0 and A1 belong to Z2. Okay. How many choice of A0? 2. Either 0 or 1. How many choice of A1? 2. Either 0 or 1. So total number of choice, that is 4. 2 into 2, 4. Okay. So the polynomial of this can be write in this way. This is Z2. So this polynomial can be written as what is A0 and A1. A0 and A1 both are 0. 0 plus, right? This thing is x square plus x plus 1. I am not going to write it again and again. A0 equal to 0, A1 equal to 0. A0 equal to 1, A1 equal to 0. Okay. This is A0 equal to 1, A1 equal to 0. And this one is A0 equal to 0, A1 equal to 0. And again, A0 is equal to 0, A1 equal to 1. And this one is x plus. And again, A0 is equal to 1, A1 equal to 1. Then 1 plus x square plus x plus 1. Okay, this thing. This is the Galois field of order 4. Similarly, Galois field of order 8, that is 1/3 degree polynomial which is irreducible in Z2, 1 plus x cube, this thing. Okay, 1/3 Galois field of order 9, Z3x divided by this 1 second degree polynomial which is irreducible over Z3, 1 plus x square. F0 equal to 1, F1 equal to 2, F2 is equal to 2. Okay, so F0, F1, F2 does not equal to 0. So 1 plus x square is irreducible over Z3. Element of this, since it is second degree polynomial, so remainder term is first degree polynomial. Here it is third degree polynomial, so remainder term is second degree polynomial. Okay. Now, how we will show that this thing is isomorphic to Z3i? See, what is x square plus 1? X square plus 1 we can write x square plus 1 plus x square plus 1. Why? Since in factor group we know that coset a plus h is equal to h if a belong to h. Okay, what is x square plus 1? This is the element of this, so this thing can be written as, so x square plus 1 is equal to what? 0. So what is x? X is equal to plus minus iota. Replace here x is equal to plus minus iota. What happened? A naught a1i plus 1 plus x square. Okay, what is a naught? A naught, okay, so this thing is 0. A naught a1 belongs to z. And what is this? This is nothing but zi. This is set of Gaussian integer. Sorry, a naught and a1 belong to z3, not z. This is z3i. A naught and a1 belong to z3. Okay, so this is equivalent to z3i. Okay, so this z3x by 1 plus x square is isomorphic to z3i. Z3i also containing the 9 element. It means a naught a1i belongs to z3i. Please wait 1 minute. So z3i is equal to a naught a1i. A naught and a1 belongs to z3. How many choice of a naught? 3. Either 0, 1 or 2, since it is element of z3. How many choice of a1? That is 3. Total number of element here in the form of a naught plus a1i, that is 3 into 3 equal to 9. So this element containing this structure containing 9 elements, z3i containing 9 elements. Okay, and in this way we can show that these two are isomorphic to each other. Okay, you can establish a 1 1 and 2 method. Okay, construct qx by x square minus 2. Similarly, x square minus 2 plus x square minus 2 is equal to 0 plus x square minus 2. It means x square minus 2 equal to what? 0. It means x is equal to plus minus root 2. So right here, element of this qx by x square minus 2 in this form. So x is equal to what? Root 2. So write it a naught a1 root 2. A naught a1 root 2, and this thing is 0. This thing is 0. Since x is what? Root 2. So this is 0. What is a naught and a1? Belongs to q. So this structure a naught plus a1 root 2, where a naught and a1 belongs to q, is written as q root 2. Okay. So this field is nothing but isomorphic to q root 2. Similarly, q root 2 root 3 we can construct as follows. Fx is equal to x square minus 3. Yes. Okay. Is irreducible over q3. See, q root 2x x square by 3 is written in this form. Again, x square minus 3 equal to 0, x equal to plus minus root 3. A naught and a1 belong to q root 2. Okay. So if we replace x by root 3, so this thing becomes a naught plus a1 root 3, where a naught and a1 belongs to q root 2. Okay, q root 2. Then this is isomorphic to q root 2 root 3. Okay. Similarly, this we already saw that zx is isomorphic to zi. Okay, x square plus 1 equal to, what is zx by x square plus 1? This is nothing but a plus bx plus x square plus 1. Okay, where ab belongs to z. If x square plus 1 equal to 0, then x is equal to plus minus I. It means a plus bi. What is x square plus 1? If x is equal to plus minus I, this is 0. abi and ab belongs to z. It means this is nothing but zi, set of Gaussian integer. Okay. Similarly, this thing become qi. So this is maximal ideal. It is maximal ideal if it is irreducible over q. So this thing can be written as x square plus 1 x plus 1 belongs to qx. X square plus 1 x plus 1 belongs to I, but x square plus 1 does not belong to I. Okay, this thing does not belong to here since it is a lower degree polynomial. Similarly, x plus 1 does not belong to this one, this thing. Okay, it means if AB belongs to P, but this implies that A does not belong to P and B does not belong to P, it means what? P is not prime ideal. Okay, see, if it is irreducible over Q, then it is maximal. Okay, but every maximal ideal is not prime ideal. Since this is maximal ideal, but x square plus 1 does not belong to I, and x plus I does not belong to I. Okay, so I is not prime. Okay, so qx by I is not integral domain. Since we already studied one theorem, if P is prime ideal, then R by P is integral domain. And conversely, if R by P is integral domain, then P is prime ideal. P is prime ideal. And if R by M is filled, if and only if M is maximal ideal. Okay, these two important theorems we already studied. Since I, what is I? I is not prime. It means by this theorem, first one, qx by I is not integral domain. Okay, so hence it is not filled. Not integral domain, it doesn't. It implies that qx by I is not filled. Okay. Next, implies that I is not maximal. See, this is I. Now, if it is not filled, then by the second theorem says that this is not maximal. So this ideal is maximal. We assume it is maximal, but later on we will show that this is I is not maximal. Okay, by using these two results and definition of prime ideal. Similarly, if fx is irreducible, it means this polynomial is reducible in qx. Right? See the result. If fx is irreducible over f, then this ideal is maximal. Remember that if fx is irreducible, then fx is, the ideal generated by fx is maximal. Okay, x is maximal and prime ideal in qx, rx, and this one, second degree polynomial. Why? Since it is second degree polynomial, so it is irreducible in q, r, as well as c. Okay, q, r, and c. What is q, r, and c? Q, r, and c are filled, and we already know that every first degree polynomial is irreducible. So x is irreducible. So by above result first, now if fx is irreducible, then ideal generated by this, that, so ideal generated by x is maximal ideal. Okay, and prime ideal also in q, qx, rx, and cx, but not in z. Why? Since z is not filled. Z is not filled. Okay, so if z is not filled, then here we are not able to say that this ax is irreducible. Okay, so this is prime ideal but not maximal ideal. This is the example. Every prime ideal is not maximal ideal. So x is ideal generated by x is prime in zx but not maximal in zx.